Here I'm going to demonstrate using source transformations to again determine a circuit parameter, and in this case we're looking for the current that is being delivered to this circuit by this 12 volt supply. The complicating factor that we have here is that we also have a dependent current source which is providing 0.7 times the current through that 24 ohm resistor to this node in the circuit. Alright, so we can still use source transformations, we just have to be a little bit careful about how we express this dependent current source. Again, with source transformations we want to make sure that we do not transform the part of the circuit that we're most interested in. So we want to try to keep this 12 volt and 24 ohm resistor intact. So we can try to transform the rest of the circuit. So to begin with, the first thing that we can notice is that this 10 ohm resistor, which is in parallel with our dependent supply, can be transformed into a Thevenin equivalent circuit where we have a dependent voltage source. Right, so I'm going to take this current supply, which is 0.7 Ix, and is in parallel with our 10 ohm resistor, and I want to determine the equivalent circuit as if I had taken this dependent supply and made it a dependent voltage source, and it's going to be in series with a 10 ohm resistor. So that means I need to determine the voltage, the value of this dependent voltage supply. So to do that we'll use Ohm's law, and V is equal to IR. Right, the current that was originally supplied by this current supply is 0.7 times Ix. Right, and the resistance across which that the potential would be developed, or through which that current is flowing, is a 10 ohm resistor. So I multiply that by 10. So that tells me that the voltage is going to be 7 times the current Ix. Alright, so we can transform dependent supplies just like we transform independent supplies. Alright, so what this does is this reduces our circuit a little bit to look like this. We have our 24 ohm resistor, our 30 down to ground, and now we have our 60 ohm resistor, and in series with that we also have our 10 ohm resistor with our newly transformed voltage supply, dependent voltage supply of 7 Ix. So now what I can do is I can combine these two resistors. These two resistors, since they're in series, will combine to give an equivalent resistance of 70 ohms. And now I have a 70 ohm resistor in series with a voltage source of 7 Ix. That is going to look a lot like a Thevenin circuit, which can be transformed into a Norton circuit. So a 7 Ix dependent voltage supply in series with a 70 ohm resistor can be transformed into a dependent current supply that is in parallel with a 70 ohm resistor. 70 ohm resistor, there we go. Alright, so again I need to determine the value of that current supply, and the way we do that is again using Ohm's law. So the current supply must be the voltage divided by the resistance, which in this case our voltage supply is 7 Ix. I'm going to divide that by the 70 ohms, which gives me a current supply of 0.1 Ix. So that means that I can replace this portion with an equivalent circuit that looks like this. So I'm going to go ahead and do that. I'll redraw the circuit. I have a 12 volt supply, my 24 ohm resistor through which Ix is flowing. I have a 30 ohm resistor here. Now I have my 70 ohm resistor, which is also in in parallel with my 0.1 IX current supply. So at this point, you could go ahead and do a node voltage method to determine the voltage at this node, or we could continue on with the source transformation route. So this method can be used in combination with all of the other methods that we've discussed. Okay, so the next thing that I can do if I want to continue on with the source transformation is recognize that I have a 30 and a 70 ohm in parallel with each other, and I can determine the equivalent resistance of those two. So the 1 over the equivalent resistance is going to be 1 over 30 plus 1 over 70, which is going to wind up being 7 over 210 plus 3 over 210, or 10 over 210. So my equivalent resistance for that parallel combination would be 21 ohms. Alright, so that means now what I can do is I can take my dependent current supply, which is acting as though it's in parallel with a 21 ohm resistor, and I can transform that back into a Thevenin equivalent circuit with a dependent voltage supply that is in series with a 21 ohm resistor. Alright, again, my challenge is to determine the value of this voltage supply right here, which I can compute using Ohm's law. Again, V is equal to the current times the resistance, in this case 0.1 IX times 21 ohms, which gives me a value for the voltage supply of being 2.1 times the current through that 24 ohm resistor. Alright, with that in hand, I can redraw my circuit one more time. I have my 12 volt source and my 24 ohm resistor through which that unknown current IX flows. And now, since I've done my transformation, that looks like that is in series with a 21 ohm resistor, which is also in series with a 2.1 IX voltage supply. Okay. Alright, so that means now to determine the current through this resistor, IX, what I need to do is I need to determine the potential difference between these 2 points. Alright, the potential difference right here, let's call this a reference node, a ground node. So if this is 12 volts with respect to that reference node, we need to know what this voltage is. All right, I can determine that current IX by applying Ohm's law. If we assume that the current is going in this direction from left to right, that must mean that the 12 volt supply is at a higher potential than this dependent supply right here. So I can write my unknown current as being IX is equal to 12 volts minus 2.1 IX divided by the sum of the resistances along the path, which is 24 ohms plus 21 ohms in this case. Right, when I do that, I can simplify some things. I wind up with 12 minus 2.1 IX over 45 ohms, which tells me that 45 IX must be equal to 12 minus 2.1 times that unknown current, which is the same thing as saying 47.1 times the unknown current must be equal to 12, which I can easily solve for my unknown current, and when I do that, I find that my unknown current is 0.254 amps. Okay, so again, as a review, what we're doing is we are taking our Thevenin and Norton equivalent circuits, and we're transforming between those two representations for the same type of circuit to simplify the circuit as much as possible so that we can wind up with a fairly straightforward and simple calculation at the end. Now, again, you can use, discussed in the course, equivalent resistances, using the node voltage or the mesh current method. So at any stage down here, when you feel like you've simplified the circuit enough, you can go ahead and then apply the node voltage or mesh current method to simplify your analysis. Oftentimes you may get to a point where you can't simplify any further using equivalent circuits, and you'll have to do that. But in this case, we were able to go all the way through. This was as far as we could get before we would have to start transforming the 24 ohm resistor, which we did not want to do because that was the primary resistor through which the current of interest was flowing.